In this video, we discussed learning outcome number 4 from lesson 4.4, which is all about permutations, but this time some items are identical to each other. So let's say you have n items that are available and you're selecting all of them, but you're selecting without replacement. But this time some of the items are identical. So you might have n1 that are alike or n2 that are alike, all the way through n sub k that are alike. Then the number of permutations, that's just a number of arrangements where order matters, can be found as follows. First, you take that number of items you have, that's n, and you take its factorial. And then you divide that by n sub 1 factorial times n sub 2 factorial, all the way through n sub k factorial, where n sub 1 are alike, n sub 2 are alike, all the way through n sub k. Those are all alike. Now, you might think that there's not an intuitive reason for this, but there's actually a really great intuitive reason for this formula. This is just a modification of the factorial rule that takes into account that you've got some identical items. So we'll talk about that in the context of an example. So let me give you your first example. This is for designing surveys, and I'll just read it to you. It says, when designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. So if they ask you the same question at the beginning and the end, and you give a different answer at the end than you gave at the beginning, well, that indicates to them that you were just thoughtlessly answering, or perhaps lying or something like that. You just, for some reason, you're not answering this same question in the same way. That would be an indicator to people that we're looking at survey results. Now, for one particular survey, they say that has 10 questions, they have 2 questions that are identical to each other and 3 questions that are also identical to each other. For this survey, how many different arrangements are possible? In order to solve this, I want to show you my piece of paper and just talk through the reasoning for this. And then we'll use a formula, and we'll see that the reasoning that we use just using intuition and the formula itself are identical to each other. They give you exactly the same answer. So I'll share my paper with you now. Okay, so you've got 10 questions. So it seems like you've got questions 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then 3 of them are identical. Oops, identical. Lost a C there. And 3 others are identical. 2 are identical, and then 3 others are identical. Okay, so maybe we'll call these guys question X and question X and question Y and question Y and question Y. I'll call this X sub 1 and X sub 2, even though they're the same question, and I'll call this Y sub 1 and Y sub 2 and Y sub 3. Okay, so they're asking the number of ways that you can arrange these 10 questions. Well, if all of them were unique, I would have 10 options for the first question, 9 options for the second question, 8 options for the third, and so on, all the way down to this. So we would get 10 factorial here if all of those were unique. That's the factorial rule. So we just multiply all of those together. But they're not all unique. Let's say x1 and x2 were here and here in a particular arrangement. So you've got these 10 positions. Let's say you put x1 and x2 there and there. Well, in one arrangement, we've got this, but in another arrangement that we've counted as separate when we evaluate this 10 factorial right here, we might have x1 and x2 in the same question in those locations as the second question and the 6th question in our survey, but maybe that x2 is over here and x1 is over there. Now, if you're saying to yourself, I thought those were the same question. They are the same question. I've just tagged them with this subscript to let you know that that was the first version of that question and that's the second version of that question. But if I flip them, this survey and this survey are identical. So we're not actually, we have no desire to tell the difference between this one and this one because that question is the same there as it is there. So we're actually counting this survey twice. We're counting this version of it and this version of it, but we don't want to count it twice. Since we don't want to count it twice, and then all of the other ways that could happen. So this could be the third question and the 10th question. So we'd count those guys twice. Or that they could be the fourth question and the 9th question, and we'd count those guys twice. To account for that, when we're counting this twice, and we don't intend to count that twice, we want to divide that out. So we're going to divide by the number of ways that we can arrange these two questions that are identical. The number of ways that we could arrange those two questions that are identical is just 2 factorial, 2 times, I've got 2 options for the first question and then 1 option for the second question. So we get 2 versions. So we divide by the 2 factorial to account for all the times that we accidentally counted these guys twice because they were identical. Now the same thing happens here with y1, y2, and y3. They're the same question. So let's just say, for example, that y1, y2, and y3 were here, here, and here. So in one of our surveys that were counted in this 10 factorial up here, you might have y1, y2, and y3 as the first question, the 5th question, and the 7th question. Now that would be indistinguishable from having y1 here and y3 here and y2 here. And that would be indistinguishable from having y2 here and y1 here and y3 here, or having y2 here and y3 here and y1 here. Does that make sense? Since we have 3 versions, 3 copies of this same question, I've counted this as separate from this, which was separate from this, and separate from this when I counted using that 10 factorial, but they're not different, or they're not separate. These are actually the same thing because y1, y2, and y3 are all the same question. Now there are a couple of other ways that we could get a survey that looks just like this. We could have y3 here and y3 here, and a y1 and a y2, or a y2 and a y1. So there are 6 different ways that we can arrange y1, y2, and y3 so that they take up the first question, the 5th question, and the 7th question in our survey. You might say, well, how many ways, well, I've listed all 6 of them right here. Say, how can you get that? Well, it's the same as the number of ways that you can put those 3 questions or those 3 items in order. You've got 3 options for the first one, and then you've got 2 options left for the second one after you decide what that is, and then you only have 1 option left for the third. So that's 3 factorial or 6. Now we don't want to call all of these separate because y1, y2, and y3, they're all really question y. They're the same question. I've just labeled them with these subscripts so I could keep track of them. But I don't want to count all of these as separate. So I need to divide out that 3 factorial because we've got 3 identical questions right here. So dividing out this 2 factorial, dividing by 2 factorial, accounts for the fact that this survey and this survey is initially counted, these 2 surveys are initially counted as different in the 10 factorial, but we mean for them to be the same because x1 and x2 are the same question. So we're going to divide out that 2 factorial, which is 2 times 1, which is the number of ways that we could arrange those 2 questions in these locations. And then over here, we're dividing by 3 factorial because you've got 3 items that are 3 questions here that are all the same. And 3 questions can be arranged in 6 different ways. So when we use this 10 factorial up here, we're counting this, and this, and this all as separate arrangements. But we don't mean to count them as separate arrangements because y1, y2, and y3 are all the same question. So we're dividing by that. Now that is exactly the same formula that we have on our sheet, it says, take the number of items that you have and find that number factorial. Now remember what that is. That's from the factorial rule. That's saying if I've got 10 questions, I've got 10 options for the first question, 9 options for the second, 8 options for the third, and so on, all the way down to 1. You say, but if 2 of those are identical, I'm accidentally counting these guys twice. So let's divide by 2 factorial, or n sub 1 factorial, where n sub 1 are alike. And if I've got 3 identical here, well then I'm accidentally counting all arrangements like this 6 times when I only mean to count it once. So I need to divide by a 3 factorial, which is the same as 6 right here, or n sub 2 factorial if n sub 2 of them are alike. And again, this number 6 is coming from the number of ways I could arrange those 3 questions in 3 positions. I could put y sub 1 first, and then y2 and y3, or y sub 1 first, and then y3 and y2, and so on. So you've got 6 possibilities. And we want to divide those out because we want to count all of these as identical. These are exactly the same questionnaire. If you were to look at them, you would say, I have the same questionnaire as my friend, even if you initially would have had this one and your friend had that one. So we want to divide those guys out, and that's how we do that. Now let's go back to the PowerPoint slides. Okay. So we've got 10 questions, 2 are identical and 3 are identical. And we want permutations. We'll use our formula. And we get 302,400 arrangements. So that's 10 factorial divided by 2 factorial, which is dividing by 2, and divided by 3 factorial, which is dividing by 6. And we get that many arrangements. Now let's look at another question. This is a classic problem, classic counting problem in combinatorics. It says, determine the number of ways that the letters of Mississippi can be arranged. Say, ooh, how many ways can you arrange those letters? Well, we've got some repetition. We've got some identical letters there. So let's see. First, we need to know how many letters we have in Mississippi. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think I'll share my paper with you again. Okay. So this time we're dealing with Mississippi. Mississippi. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So n equals 11. But when we're looking at that word Mississippi, you've got one M, and then you've got 1, 2, 3, 4 I's, and 1, 2, 3, 4 S's, and 2 P's. Well, if these were all unique letters, we'd have 11 options here, 10 options there, 9 options there, because we're selecting and then we're not putting those letters back. We're not putting them back in the bag of letters if we were selecting from a bag. So you got 11 here, and now you've got 10 left to choose from for the second letter, 9 left to choose from after that, and so on all the way down. So if they were all unique, the count would be 11 factorial possible arrangements of the letters, but they're not unique. We've got 4 I's, 4 S's, and 2 P's. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's just say that the P's were first. And I'll label these P1 and P2. So let's say we have P1 here and P2 here. And then all of these are going to be identical in this arrangement and in this arrangement. I have P1 here and P2 here in this arrangement, and I have P2 here and P1 there in this arrangement. This 11 factorial is counting those as separate arrangements. But a P is a P. It doesn't matter that we're calling this P sub 1 and this one P sub 2. This arrangement, if I was just looking at the letters that were left over, I'd have P, P, and then something else after that. I want to count those as separate. So in order to count those as separate and any other pair as separate, we want to divide this 11 by 2 factorial. And the same is going to be true about those 4 i's. So 4 i's lead to 4 factorial possible arrangements. So let's say you had an I here, an I here, an I here, and an I here. Well, you could arrange them that way, or you could arrange them this way. Or you could arrange them this way. And so on. Now, it would take me a little bit longer to show you all the possibilities, but you've got 4 different possibilities for that first position, 4 different i's for the first position, then you've got 3 different i's for the second position, 2 different i's for the third, and only 1 I left after you've selected these 3. But if those i's are at those locations, we're counting this is the same as this, and that's the same as this. We're actually counting all of these guys as the same, because when we look at it, we don't see an I sub 1, an I sub 2, an I sub 3, and an I sub 4. We just see an I, an I, an I, an I. We just see 4 i's. So we need to divide out all of the times we're copying or we're counting those as separate when they're actually the same. And that happens 4 times 3 times 2 times. So that's 12 times 2, which is 24 times. Or again, that's that 4 factorial. So we had 2 p's that were alike, so we needed to divide by 2 factorial because we're counting these as different when we don't intend to. We've got 4 i's that are alike, so we need to divide by 4 factorial because we're counting arrangements like these as alike when we don't intend to. And you're going to have 4 s's that are alike as well. So we've got an S1 here, an S2 here, an S sub 3 here, and maybe an S sub 4 here. That could easily have been arranged this way instead. And those would be different because this one has S sub 2 and that one has S sub 3. When I actually look at it over here, this is just going to have a P, that'll be P, P, S, S, I, S, I. I guess there's going to be our M there finally, S and I. So that's the arrangement that we're talking about. So we had 2 p's that were alike, so we divide by 2 factorial. We have 4 i's that are alike, so we divide by 4 factorial. 4 s's that are alike, so we need to divide by 4 factorial there. And we could divide also by 1 factorial, but it makes no sense to divide by 1 factorial. It's just dividing by 1. It doesn't change anything. Okay, so according to our formula, this is the number of ways that we can rearrange the letters in Mississippi, given that you've got 4 s's that are alike, 4 i's that are alike, and 2 p's that are alike. So let's go back to our slides. Okay, I just use applying that formula. You've got 11 letters, 4 i's, 4 s's, and 2 p's. And if you actually work that out and do the division, you end up with 34,650 arrangements, which is significantly less than 11 factorial arrangements, which is what you would get if every single letter were unique. But since we don't have unique letters, we have to use this formula instead. And again, we're using this formula because we're accounting for different arrangements that look like this. We intend for this and this to count as the same thing. When in reality, if we treat all the S's as distinct and all those P's as distinct and all the I's as distinct, if we count them as distinct as we did up here with that 11 factorial, yeah, well then we're counting these as different. And we don't want to count those as different. So in order to not count those as different and say that's actually exactly the same as that, we need to divide by that 2 factorial, the 4 factorial, and the other 4 factorial. So that's it for our lesson about permutations with identical elements. I'll see you next time when we'll talk about combinations.